Welcome to Study Guide Forum. This is another time for us to look into, we want to look at electrolysis, the Faraday's laws of electrolysis. So in this law of electrolysis, we find out that the first Faraday law of electrolysis says that the amount of elements deposited during an electrolysis is directly proportional to the quantity of electricity that pass through the electrolytes. So that means the quantity of the mass deposited is directly proportional to the quantity of electricity. From our mathematical symbols there, analysis here, we have that M is directly proportional to Q, where Q, mass, M stands for the mass, and then Q stands for the quantity of electric current. Now we know that quantity of electric current, you can also get it by quantity of electric current, which is Q, can be calculated by current times time. So if it's so, it means that mass is directly proportional to electric current and also directly proportional to the time. So in that case, if we are to apply the if we are to go by this, since we know that where do all of them here stand for the word quantity of electricity, and then what remains now is that mass is equal to, if we apply the constant which we know as a electrochemical equivalent, which has the symbol, and current and time. So which means mass is equal to this electrochemical equivalent times current times time. So in that case, if you want to calculate the mass deposited with this, you can also get that. So that means if we want to calculate the current in this case, we can also do it this way. Current will then be mass over what, and then time can also be mass over. So with this, you can also get what, if you want to calculate the electrochemical equivalent, you can also do it this way: mass over what, and then get the electrochemical equivalent. So the next one we're going to look at here is the Faraday's second law of electrolysis. In the second law of electrolysis, Faraday states that the law states that when the same quantity of electricity is passed, electric current is passed through electrolytes for the same time, that the mass of different substances discharged or deposited at respective electrodes are inversely proportional to the charges on the ions of the elements. That means, for example, let's say that we have something like silver and silver which has this, and copper which has 2+. So in that case, the mass of silver deposit, if the same quantity of electricity pass through them, the mass of this discharge will be while that of copper will then be x. That means it's inversely proportional to the ion of the charges. So in this case, what we're going to do now is we're going to try some example questions. Even after this one, this first video, we're going to look at some other calculations that have to do with this, so that to help us to really be rooted in it. And then I want you, if you have not subscribed, make sure you do that. Share and like. So let's see. Let's look at some calculations that will help us in this to understand it better. So here we have a question. Say that calculate the amount of gold deposited when a current of 10 amps is passed through a solution of gold salt for 4 hours. If the same current is used, find the time taken for 12 grams of gold to be deposited. We have the relative atomic mass of gold and the 1 Faraday, which is this. Now, before we solve this question, I want to so I want to really look at this Faraday. Say that 1 Faraday. Now, 1 Faraday is the quantity is measured in coulomb, as you can see here, and it also means that um, one electron to discharge or deposit one electron, it requires 1 Faraday. If it's for divalent element, it will require about 2 Faradays. If it's monovalent, it has a 1 Faraday, which is equal to this. Just like in gold, gold we know that is a univalent electron, and for the current to be discharged, gold will require so gold will will gain one electron to discharge gold gold metal here, to discharge gold metal. So what it simply means that since it's a one electron it requires, it means that it requires 1 Faraday, 1 Faraday of electron, which is equal to coulomb. So looking at that now, it means that to deposit this, we have is equal to 197 grams of what? Gold. So now what we're going to find out here is the quantity of electricity that we need. This quantity of electricity is what we need to discharge 197 grams of gold. So to get the quantity of electricity we need to discharge what is stated there for us there is that we know that quantity of electricity is always, so we have our time is always in seconds. Our time is always in seconds, and our current is always in amp. So looking at that, we have our current, which is 10 times time, which is 4 hours. Since we are going to get it in we're going to convert it to seconds, it means that we're going to multiply by, then we'll have 144,000 coulomb of electricity. So now the next thing we're going to do here is that since we know that this is what we have for a unit mass of gold, that is for 197 gram of gold to be deposited. So what we're going to find out now, how many grams of gold will be deposited here. So in that case, we will say that 144 will then be equal to 197 over, what am I doing, times 144. That will give us this is a gram, the mass of gold that will be deposited. Now the next question there said that find the time taken for 12 grams of gold to be deposited. But now we're looking at the time. It will take to get this one done. So the time taken now, you say that if the same current is passed through there. So from this our first equation, from this our first question that we have solved, we discover that um, 293.7 grams of gold required 144000 coulomb. So now, what will these 12 grams take? Since we are looking at it based on the same number of the same currents is passed through them. So what we do here is, so then the next thing we do, by dividing, we will have our result to be 5878.2 coulomb. That is the quantity of electricity that we require to get 12 grams. Now, that is not all. That's not just where we are going to end again. So then we know that quantity of electricity is always current over what? Current multiplied time, which is equal to the one we have here. So, and now we have our current. Our current in this case is what? 10 amps. So that if the same current is passed, that means if we use the same current, that means we're going to get the time now. Then we're going to substitute. If we substitute for that, we have the quantity of electricity. Okay, we're going to substitute for that. If we are substituting, we know that it's equal to what? Quantity of electricity. That means time, current, we know that the current is what? And then time is what we don't know, times time, we don't know the time, and then we have our quantity of electricity to be what? And 5878.2 coulomb. So by dividing, time now will be divided by 10. Divided by 10, what we have here should be 587.82, and that is seconds. Since we always talk about seconds as the quantity of electricity we need to discharge the 12 grams of gold. Thank you so much for this time and for coming this far. I want to encourage you to subscribe and also visit our playlist. There will be a lot of so many other videos to enjoy so much. Thank you.